So welcome back to the class Computational Neuroscience. We look again at a model of associative memory. And the question we would like to ask now is, we have seen that we can store several prototypes, but how many prototypes can really be stored? So here again the rules of the game in the Hopfield model. I have a dynamics, binary state variables, and this dynamics includes weights, and the weights are just the sum over the different contributions of the different patterns. And I added here a 1 over n in front, which has no real meaning because I look at the sign afterwards, but it simplifies a little bit the calculations. So what we want is that we start in an image that's noisy, that's sort of a noisy version of one of the prototypes, and then it corrects and gives back the pure prototype. That's the task. However, that's a little bit hard to calculate. So we make a really minimal condition. Suppose you start directly in prototype. Say you start in prototype number 2. Then at least, if you run the dynamics, you should not move away from the prototype. You should stay in the prototype. Okay? So we assume we start in one of the prototypes, and the minimal condition is that the pattern should stay. Attention, retrieval really requires more. We want pattern completion, but this is really a minimal condition. So let's look at this minimal condition and assume that we start directly in one of the patterns, say pattern number 7. What does this mean? This means that for each j, the value of Sj is equal to Pj of pattern 7. So at time t, each neuron is in the state that's consistent with pattern number 7. Now what do we know about the weights? Well, for the weights we have this formula which I just plug in. So I have a 1 over n sum over mu pi mu pj mu. And then I copy the sign function and the summation sign and close the brackets. So suppose we have m patterns. So the sum runs over all the patterns from 1 to m. M is, for example, 25. And as we sum up, we have mu equal 1, 2, 3, 4, 5, 6, 7. But 7 is special. And then we continue 8, 9, 10 until m. 7 is special. Let's pull out this special pattern, and therefore I split it up. I say, in this sum, I have the case mu equals 7. And then in this sum, I have the case, I sum over mu, but mu should not be equal to 7. It's basically all the rest. So let's look at the first part. Sign off. I have sum over j, I have a 1 over n, and now here I have mu equals 7. So I have pi 7, pj 7, pj 7. And then I have the rest, which I can just copy. So I have 1 over n, sum over j. I have pi mu, pj mu, pj 7. Now let's look at this term here. There's something interesting because pj7 times pj7, this is a square. So pj is plus or minus 1. Suppose it's minus 1, I have minus 1 times minus 1 gives 1. If it's 1, I have 1 times 1. So whatever the value, the square, pj7 times pj7 is 1. So this is always equal to 1. I have n of these terms because I sum over j. So in the end, the 1 over n will go because I have n terms. And what remains is just pi7. Now let's look at the other term. I have a plus, then I have a sum over all patterns mu, except pattern 7. I have a 1 over n, then I have a sum over j, and then I have pi mu, pj mu, pj 7. So this term looks complicated, but for the moment let's make it just a little bit more complicated. The reason why I want to do this will become clear in a minute. So we have seen before that pj7 times pj7 is always 1. Same is true for pi7 times pi7 is always equal to 1. So I can plug this in. I can always multiply with 1. Let's write one of these pi7s here and the other pi7 here. Nothing has changed. I've multiplied with 1. Now the advantage is, now you see I have a term here pi7 and a term here pi7. It's the same. Now, little aside, think of sine of -1 times a. That's the same as -1 times sine of a. That means if I have a number -1, I can just pull it out. If I have a number +1, I can pull it out anyway. So I can take this pi7 and write it in front. Equals pi7. And then I have the sine. I've pulled this out. This is 1 plus 1 over n. I've pulled this out. Sum over mu, but not mu equals 7. Sum over j. pi7, pi mu, pj mu, pj7, and I close. This is the end of the calculation. May look horrifying to you, but it's actually quite illuminating. Let me try to explain it a little bit. So we said we start directly in one of the patterns. So we had that Sj at time t is equal to the pattern pj7. Now what we find is that Si at time t plus 1 in the next time step is equal to pi7. Well, if this guy here is positive, then the sign of this is just 1. So neuron I in the next time step is in pattern 7, stays in pattern 7, if the term in square brackets is larger than 0. This is what we want. But we don't necessarily have this. So I can rewrite this by saying this whole term here, let's call this minus ai7. It's just a constant a parameter a, and I need the index I because I is here. I sum over j goes. I sum over mu goes, but the 7 remains. So I have two indices, and this red thing, I define it as minus ai7. So what can we say about this guy here? Well, it's a multiplication. I have here plus minus 1, plus minus 1, plus minus 1, plus minus 1. So the whole thing inside here is plus minus 1. And then I sum over n of these plus minus 1, and I sum over m minus 1, because I don't have this pattern number 7 in there. So basically, what we have is plus 1, minus 1, plus 1, plus 1, minus 1, plus 1. So I have a random walk. I go up and down, plus 1, minus 1, in a random fashion. And I do this over how many steps? Well, it's n times m minus 1 steps. So what we want is that this random walk stays limited so that this part here inside the square brackets is positive. So let's look at it at the next slide. The minimal condition that we had is we start in a pattern, say pattern mu, in our case pattern 7, and then we want that this pattern stays. And we find that this is possible if this variable ai nu, now for arbitrary pattern nu, in our case it was 7, is smaller than 1. Because we want this to be positive, that's what we want, and therefore a must be smaller than 1. Now for random walk, which is completely unbiased, the mean will always be 0. But if you do 500 steps, you may actually end up close to 0, but not exactly at 0. and you have a certain width of this distribution. And this width or standard deviation is proportional to the number of steps. How many steps do we have? Well, we have n times n minus 1 steps. So with a random walk with n times n minus 1 steps, the standard deviation is proportional to the square root of the number of steps, but then I have a factor 1 over n in front. So I want a to be smaller than 1, which means the standard deviation has to be small. The standard deviation with step size 1 over n is 1 over n times the original standard deviation, which basically makes n minus 1 over n. So what we see here is that if the number of patterns, number of patterns, is of the same order as the number of neurons, then we run into a problem. So basically, if you work with 10,000 neurons, the number of patterns should be much smaller, for example, 200. Then the standard deviation will be very small, and for nearly all the pixels, for nearly all the neurons, we will be error-free. The storage capacity asks the question, how many prototypes can be stored? The answer is, we can store a number of prototypes that should be smaller than the number of neurons in the network, significantly smaller. Then we will be fine. So, we work with random patterns, and in this case, we can have a number of patterns, m, that's small compared to the total number of neurons, but at least, if you have 10,000 neurons, we can store 200 patterns, which is quite a lot. Now imagine the size of our brain, so it's not surprising that we can store a huge number of different patterns in our brain. The size of the English vocabulary has been estimated to 100,000 words, would be 100,000 different items. It's a lot of different concepts, but why not? We are able, in principle, to store this in our brain. So what I wanted to convey this week is this idea that memories are stored in the network of neurons, more precisely in the connections between the neurons. And we can retrieve this memory, and in the same network of neurons, we can store many, many memories. Specifically, in the Hopfield model, each memory concept, each memory pattern is a random pattern. It's highly pre-processed. But for these random patterns in a network of n neurons, we can store maybe in a network of 10,000 neurons, we would be able to store 200 or 500 different patterns. Now, importantly, there are simple computer algorithms that can retrieve a full concept from partial information. However, what I've shown here is that in the Hopfield model, we don't need a central controller. It's just the interaction between the neurons that makes the network converge to the most similar pattern that restores the full concept from partial information. So models of memory, models of associative memory, models of auto-associative memories have a long tradition. I've presented here a version of the Hopfield model, but the tradition goes back much further. As you see on this slide, there is David Wilshaw, there is work of Kohonen, of Little, of Anderson, and many others who have contributed to our understanding of how the brain could potentially form memories. You find all the information in the book on neuronal dynamics, for which we also have an online version. See you again next week.